Okay, so let us start our discussion on Kallen-Lehmann spectral representation, and we will continue from where we left last time. So just to remind you, we were analyzing this object okay, and where phi could be elementary field, the field that appears in your Lagrangian, or phi could be a composite field. Okay, and we showed that, let me go back, that this can be written as this spectral density integrated over spectral density times free propagators, but this time the mass that appears in the free propagator is the mu square, okay, and mu square is not a mass in the physical theory, okay, it is something which you integrate over, okay, so mu square takes all possible values from 0 to infinity. So this object takes this form. That doesn't mean that you have particles of mass mu square in your theory, okay, that's not something it means. It just means that this quantity can be written as an integral over mu square of the spectral density times the Feynman propagator, okay, where this propagator, instead of having mass m, it has mass mu square, okay, that is the notation here, and you have to integrate over all of these. Let's see, correct, okay. Also, let me write down the definition of rho tilde of q. Rho tilde of q is this, okay, let me write it down. So rho tilde of q is 2 pi cube times, you have you are summing here over all the states in the physical theory. All this by all the states means I have taken the states n to be the eigenstates of energy momentum of p mu, okay, energy momentum vector p mu, and this is what delta 4 q minus p n times omega, let's what was it, phi 0 get n, okay. Okay, and we had argued that rho tilde of q is a Lorentz invariant object because this factor here, this is Lorentz invariant, okay, and this factor is Lorentz invariant. So this entire thing is Lorentz invariant, and also it is non-vanishing only if q naught is positive, okay, and that is why we also wrote it as rho of q square times theta of q0, okay. And then let's see what else. Perfect, that's all. Now we'll continue from here. Now we want to you see rho tilde of q, or equivalently rho of q square, that gets contributions from all possible states n, all the states like single particle states, multi-particle states, okay. So single particle state, 2 particle state, 3 particle state, okay, in general everything will contribute. So what I want to do now is to filter out the contribution of single particle states. So contribution of single particle states to rho tilde of q. Okay, and these contributions I will call as rho tilde q single particle. Okay, and similarly rho of q square I will define rho single particle with this argument q square. So that's what we are looking at. Okay, so what is that object? That object is 2 pi cube, so that 2 pi cube factor here. Then summation over n, but now we have to appropriately replace this sigma over n by the measure that you have, which we have discussed earlier, is d cube k over 2 pi cube. I hope that's correct. No, that's not correct. No factor of 2 pi cube. We had just 2 omega k. You remember we had long back discussed that this is the appropriate measure for single particle states. Okay, because the n label n is not discrete; it's continuous. It's the single particle states have continuous momenta. So you have an integral, and this is what gave you the correct measure. Okay, that is fine. Now I should put delta 4. So delta 4 q minus, now Pn gets replaced by k. Okay, and then you have omega phi 0 k, okay, mod square. That's fine. And then other contributions, not to this but to rho tilde q, coming from multiparticle states. Okay, this is nice. This is good. Yeah. Now what I will do is I will utilize the following result. Let me recall. So recall that we had shown d cube k over 2 pi cube 1 over 2 omega k. This we did in the previous course, the first course, is same as d4k over 2 pi to the 4 times 2 pi delta plus k square minus m physical square. Okay, this is what we had done, where here m physical is what appears in omega k, where omega k is k square plus mp square. Okay, and this mp square is what is appearing here. So and here omega k is the same object. Okay, so this I can write as 2 pi cube times, you have 1 over 2 pi cube multiplied here, so I have another factor of 2 pi cube times d4k over 2 pi to the 4, okay, times 2 pi delta plus k square minus mp square. Okay, and remember delta plus is this k square minus mp square is delta of k square minus mp square times theta of k 0. Okay, let me close the window. Okay, so this factor is here, and then I have still a delta 4. Okay, looks like again a problem. Okay, so now I will do integral over k, and this 2 pi cancels this 2 pi 4, which leaves a 2 pi cube, and that 2 pi cube I can cancel with this 2 pi cube. So I have a 2 pi cube here, okay, this one left. And then when I integrate over k, the k get forced to become q, okay. So here in this delta plus, which is same, let me write delta plus, it becomes q square minus mp square times omega phi 0 k mod square. Okay, and remember delta plus has a theta q0 in it. Okay, so from this I can then read off what rho of q square is coming from single particle state, that is 2 pi cube, okay, times times this delta of q square minus mp square, okay, because rho tilde is rho q square times theta naught. So that theta q naught I am taking away, and then you have this factor, this Lorentz invariant factor. Okay, so that's nice. When I look at rho of q square coming from single particle states, it is proportional to delta of q square minus mp square. Okay, and it will have a nice consequence for the g tilde of q. Okay, when I take the Fourier transform of this object. Okay, I'll give you an exercise to do the same integral which I have done in a different way. So show that delta of q square minus mp square times theta of q naught is equal to 2 omega q delta of q naught minus omega q times theta of q naught. So this time you will not utilize this result here, okay, this one which I used, but you should now show this, and then you can utilize to arrive at the same expression of rho of q square. Okay, and proving this you will have to actually delta of f of x, okay, where f is some function of x, and this is delta of x minus x naught over f prime, the first derivative at x naught, and you have to take a modulus of it. Okay, so signs are not counted here. So where x naught is a 0 of fx, okay, meaning if you put x equal to x naught in the function, it gives you 0. Okay, and you may have several zeros, and in that case we should put a label I to label those zeros, and I should sum over all the i's. Okay, so that's something you should do and arrive at the previous result. Okay, good. So what next? So what did I write? Okay, now this quantity rho phi naught k, I will define it to be n over 2 pi cube. That's a constant, and I will define coming from single particle states, I will define it to be n over 2 pi cube, okay, where n is a constant. So what do you get? You get rho coming from single particle states is n times delta of q square minus mp square. That's what you get right here. So, here 2 pi gets cancelled and you have only delta function times n. Okay, just to be sure that I am not leaving, I will just write as rho of q square is, so now this is for the full thing, not just for single particle states, q square minus mp square plus contributions coming from multi-particle states. Okay, excellent. Now, let's look at the case where your field is an elementary field phi that appears in the Lagrangian. Okay, but the structure is the same. This you have here n, and we had earlier defined for the case of elementary field phi that this omega phi of 0. Now, I am not using a boldface phi, but I am using this phi. Okay. K, this is what we call as z, right? Z over 2 pi cube. Okay, so n gets replaced by z when you are looking at the elementary field phi. So, what do we have then? In that case, when I am looking at spectral density for the case of this elementary field phi, that rho of q square is z times delta of q square minus mp square plus contributions coming from single particle states, multi-particle states. Okay, where for that's what we are doing now. Okay, good. So, we got the rho of q square, which is nice. Okay, let's analyze a little more. So, let's also ask what happens to the contributions from 2 particle states. Okay, so rho of q square, let me try to plot this. So, rho of q square at moment looks like this. That when you are at the physical mass, okay, the square of the physical mass, meaning q square is equal to mp square, then you have a delta function here. Okay, and I am just drawing it like this, but of course you have to take the limit in which it becomes infinitely sharp. So, that is the delta function. So, there is no contribution to rho of q square if q square is less than mp square. Okay. Now, let us ask what happens when you go above mp square. Do you have contributions coming from all these values? Okay, and the answer is no. Why? Because where is it? Yeah, contribution from, not from here. Where can you see? Yeah. So, you can see this way. Not here. Okay. So, look here. Here we had a sum. We had a sum over all the states of which are eigenstates of p mu, and we singled out first single particle states, and this brought in d cube k. Okay. So, you have 3 integrals, and you have a delta 4, which basically 4 delta functions, right? Delta of q0 minus k0, delta of q1 minus k1, delta of q2 minus k2, and delta of q3 minus k3. So, 4 delta functions and integral over 3 variables, okay, dk1, dk2 and dk3, and that leaves behind one delta function, and that is what you are seeing there, okay, in the final result. That is what you see here. Now when you look at the multi-particle states, let's say two particle state, the delta function, you still have 4 deltas, okay, but now you have integral over d cube k1 and d cube k2. Let's say the momenta, individual momenta are k1, k2. Then when you integrate, you have 6-dimensional integral, but the delta function is 4-dimensional, so it gets used up, and you are still left with 2-dimensional integral. So there is no way you are going to get a contribution to rho of q square from multi-particle or from two particle states, which will be proportional to a delta function. That's not going to happen, right? Because of this counting. 6 integrals, d cube k1, d cube k2, 4 delta functions, so you are still left with 2, okay, and that you integrate over these functions, these objects. Okay, so one thing is clear, it's not going to be proportional to delta function. The another thing that you can observe is when you do integral over k1 and k2, and it's k1 and k2. We are labeling the momenta by k1 and k2, so Pn takes those values, okay. So you have two particles, and we ask, so this will have this state will have some invariant mass, okay, some q square, or k1 plus k2 whole square is what we are calling as q square, and we ask what is the minimum value that q square can take, okay. And because you have a two particle state, the minimum value that q square, which is the sum of the momenta squared, okay, or if you just think of these, sum of the momenta squared will be the minimum value will be taken when both these particles are produced at rest, okay. So imagine you give a momentum for momentum q, okay, and then both the particles are just produced at rest, they are not moving at all, okay. So they just have energies due to their masses, but there is no energy carried due to the momentum, and that is the configuration which will provide the lowest value of q square. So what is that configuration? So if q, let's write as q1, k1 plus k2, these are the labels, not 3 vectors, sorry, k1 plus k2, okay, because I am looking at a two particle state, so it carries two labels, k1 and k2, okay. And what's the minimum value? The minimum value is when you have the 3 momenta of both of them equal to 0, okay, and in that case q square is just k1 0 plus k2 0 squared, but k1 0 is mp, k2 0 is also mp squared, so that's 2 mp square, okay. So you see that there is no contribution to rho of q square coming from two particle states if the value of q square is lower than 2 mp square. So here you have 2 mp square, which is basically 4 mp square, and then you start getting contribution from here. There is no contribution from the intermediate values of q square, and you, as I said, this is not it will not be some delta function, it will be some distribution, okay. So contribution from multi-particle state starts from here, okay. So it will look something like this. Now it is still possible that in a general theory which you are doing, you have bound states, okay. For example, if you are doing electrodynamics, you can make atoms, right? You can have or even let's say an electron and a positron, okay. You can form a bound state. Now bound state is more like of a single particle state, right? Because that bound state is going to move as a whole. It's not, these two are not in, you can assign a momentum to that entire atom, okay? You can assign an energy to that entire atom, okay? And you can see that that bound state as a single particle, okay? If that is the case, then whatever I have, again not if, okay, given that whatever I have said before this implies that we should also get delta functions at those bound states. Okay, so if there is some bound state in the theory, for example, if you can make some atoms with positron and electron or whatever, then it will also lead to some delta functions. Okay, it could be more than one depending on how many bound states you have. So these delta functions come from bound states. Okay, this is from our single particle states. And this continuum is coming from multi-particle states. Okay, this is good. Okay, I'll talk about looking at the Fourier transform of this object in the next video.